Welcome. This is the Water and Irrigated Agriculture portion of the Water, Civilization, and Nature MOOC, addressing water challenges of the 21st century. Hi, my name is James Pritchett. I'm a professor in agricultural and resource economics at Colorado State University. I've been trained as an ag economist, working in the area of agriculture and water resources, not only how we can use that on the farm, but also what it means to local communities in order to have that irrigated agricultural base. And then maybe even at a broader scale, understanding policy issues that influence irrigated agriculture and water resources. So that's the perspective that you'll get from me today, is thinking about things like an ag economist. We're really going to provide you with an overview of several agricultural economic issues and agricultural issues as it relates to water resource economics. It won't be in terrible depth or in terrible rigor, but instead it's an introduction to issues, and you'll have the opportunity to dig a little deeper into those issues by enrolling in other courses. Here's some key takeaways that I want you to think a little bit about. First, by the end of this session, we want to understand that water is a complex natural resource, and it joins people and food, fiber, cultures, industries, and the environment all together. And it's important to think of water as being this interconnected activity or set of activities, so that when you change one, it influences all of the others. And these activities are influenced by external forces, things like climate change and the laws and institutions that we use to allocate water. The way that agriculture uses water will have to necessarily change in the future because of those external forces that I mentioned. And we'll talk a little bit about some of the things that we can do in order to take advantage of opportunities in the future and to fend off some challenges. Opportunities do abound for meeting those agricultural water challenges, but all of those are going to require collaboration by individuals within the watersheds and by different stakeholder groups. So let's get started thinking a little bit about water and irrigated agriculture. The first thing I'd like to do is give you a snapshot of how water is used in irrigated agriculture. Important to note that agriculture uses water throughout its supply chain. For instance, feedlots will use water in order to produce cattle. But we're mainly focusing on the crop side of things with this particular presentation, so that's where the emphasis will be on irrigated agriculture. I wanted to give you kind of a hydrologic view from the hydrologic cycle, a view of how water is used in irrigated agriculture. So the diagram that we have represents sort of an upland slope on the left-hand side and a river system that runs downhill to where there is an ocean down at the far right-hand side and a municipality. Rain falls in those upper uplands and is collected in lakes and streams, maybe even reservoirs in that area. And then the water trickles down so that it can be used by farms. Surface water, using that water that flows down through the river system, is one way that water can use farms. But also that water will percolate down into the groundwater, and those farms may use wells, high capacity commercial wells, in order to pump water up and irrigate crops with those. Whether it be via surface irrigation or be via the groundwater irrigation, there will be water that will apply to those farm fields, and those will make its way back into the river system. It won't be completely used by the crop. That water can flow back into the system and be reused and reused again and reused again as it travels downstream until it eventually meets that water area. So one thing that's true is that if agriculture uses water, it can use it from two different sources, that being the surface water and the groundwater. That agricultural's use of water can also be used by others, and agriculture can use the return flows of water that comes from other farms and comes from other cities. So there's really a complexity of uses that take place. We've gone so far as to categorize these uses of water in agriculture into a variety of different areas. One of those areas that we categorize water into is blue water, and that's fresh surface water or flowing water and groundwater that's been preserved in the groundwater level. So this is water that we're going to bring up, that we're going to use for crops. This is different than green water. Green water is precipitation that falls down and that doesn't run off the land or isn't used to recharge groundwater. So it doesn't flow into the stream. Instead, crops use it where it is. And crops use that water in an evapotranspiration process in order to grow its foliage or to grow grain. The last type of water classification is gray water, and that's the fresh water that we use in order to assimilate a load of pollutants, actually dilute those pollutants in discharged water. So 3 different water uses: blue water, green water, and gray water. One thing that I think we want to take away is that water is really distributed throughout the world in varying amounts. And that can both be in terms of the green water, which is in the upper portion of the map of the world, where you see green water distribution. Darker colors of green represent more water. Blue water distribution, which is also spread unevenly, and that's the flowing surface water and some groundwater. Darker shades of blue indicate more blue water. And gray water, which is also unevenly distributed. But one thing you might notice is that it really fits with populations, because we use our fresh water to discharge in areas where there tends to be heavy populations. So water is sort of spread unevenly throughout the world, and yet, with the exception of really gray water, it doesn't always match up where the people are, which can lead to water stresses. So irrigated agriculture, well, it needs to be located where that water is. And in areas where there is significant population or other competing uses for those types of water, that's where we may have some scarcity. One of the things that's also true about agriculture is among that water that's available, the green water, the blue water, and the gray water, among that water that's available, agriculture really is the largest user of water and withdraws the most. In this chart produced by the FAO, you can look at, for the world, that's the far left-hand side of the charts, and different other areas or sectors, what their withdrawals are by the type of industry that's there. So agriculture is the very darkest brown, sort of the middle brown is industrial use, and municipal use is the lightest shaded brown. Agriculture worldwide will extract or withdraw about 70% of all the water that's available within the world as a percent of all water withdrawals. Different regions use more or less water for agriculture depending on how much is available and how much is actually fed as precipitation, and to the extent that they have industrialized sectors. So in developed countries like Western and Central Europe, you see that on the far right-hand side of the chart. They tend to use more water as a percent of withdrawals for industrial use and municipal use compared to their agriculture. But in the least developed countries, which is the far right-hand bar, those countries tend to use most of their water for agriculture, and really agriculture is generally an important base industry in those countries, so that makes sense to us. So agriculture is by far the largest water user, and it uses it in order to produce crops that later go to feed those individuals in municipalities. I think that one thing is true is that individuals often think that cities use the most amount of water, but in truth their withdrawals are small compared to what we use for food, which is an indirect demand of those cities. So why is irrigation important? Why do we need that much water in agriculture, and why is it important that persists? Well, I think one thing that's important is on the front of everybody's mind is that we use irrigated agriculture in order to meet global food needs. So it's true that dryland agriculture, where precipitation or green water just feeds that does provide some of the water that we have. Let's look about it in this diagram. That'll help us out some. Because we'll look at rain-fed agriculture versus irrigated agriculture and find out that irrigated agriculture is actually the area which uses water to produce the most food for this system. So on the left-hand side of that diagram, we have precipitation. 100% of the precipitation falls down to land and soil. About 65% goes there, and that's green water. And then 35% goes to lakes, rivers, and percolates down into the groundwater. That's blue water. The green water can be used for rain-fed agriculture, so precipitation falls and plants take it up, and then they evapotranspirate that and use that to produce some of its foliage and some of its crop. And so for that rain-fed agriculture, about 80% of the agricultural land produces about 60% of the food. But when it comes to the bottom portion of that diagram, where we have blue water and gray water, lakes, rivers, and groundwater give that blue water, and gray water from return flows from domestic and industrial water use also contribute to irrigated agriculture. Irrigated agriculture only has 20% of the agricultural land, but it produces 40% of the food. So you can see that there's really an increased productivity that is associated with irrigated agriculture, because you can use water more intensively to produce crops that go on to meet global food needs. The other thing that's true about this is that rain-fed agriculture, well, that faucet can turn off every once in a while. We can have droughts, and then cropping suffers. But when it comes to irrigated agriculture, to the extent that we've managed the supplies within reservoirs and within lakes, and to the extent that we can economically extract that from groundwater, irrigated agriculture is a much more reliable supply of food. So not only does it produce more food per acre because of its intensive production, but also it's more reliable, and that reliability is really important for meeting global food needs. The other way that water-short areas are able to obtain water is not necessarily through a direct flow or by a reservoir or by a pipeline, but instead they may virtually ship water to areas where there isn't much by shipping food. So we grow food in areas where water is abundant, or we're very efficient in our use of water, and ship those to areas where perhaps they're not as abundant or not as suited for producing agriculture. And that's what this chart shows, is global water savings associated with international trade. That if you can ship the products, then in essence you're shipping water from one area to the next. In the left-hand side of that chart, in the United States, there's a lot of blue water that's used in Western irrigated agriculture, and that can be shipped to areas around the world, including Japan and other spots on the far right-hand side of the chart, where less suitable agricultural conditions are found and less water is available for agriculture. So virtual water, shipping from one place to another, is another way that we can meet those global food demands, and one of the reasons why irrigated agriculture in one part of the world is important for feeding other parts of the world. I mentioned earlier that irrigated agriculture is really more productive in producing goods relative to rain-fed agriculture when you compare everything on a per acre by per acre basis. And I think in the United States this really shows up in terms of the revenues and the value of marketed agricultural products that's sold when you compare irrigated farms to dryland farms. So let's take a look at this chart produced by the Economic Research Service using statistics from the National Agricultural Statistics Service. And let's look for evidence that irrigated agricultural crop production might be more efficient, more productive on a per acre basis or a per farm basis than dryland farms. So the far right hand side of this chart, that's dryland farms. The middle portion of the chart is irrigated farms, and all farms represent that first column on the left hand side after the labels. If we look at the market value of agricultural products sold, measured in thousands of dollars, that's that first row. And for all farms in the United States in 2007, that appears to be more than $297 billion of agricultural products that were sold, or about $143,000 per farm. Irrigated farms, relative to what that average is, they produce about $344,000, and that's a mix of irrigated and dryland cropping. Or if it's just irrigated cropping, that's about $349,000. So a greater value of crops has been produced in those areas. And it's especially true that in the United States that if you produce a higher value of crop, you're more likely to have irrigation because you have more at risk associated with the value of that crop. It's also true when you compare that to dryland farms, that far right-hand column, that the value of market goods and sold is only about a third for the dryland farms compared to those irrigated farms. So in terms of producing the assets or producing the value of crops, it's much higher with irrigated cropping compared to dryland cropping. The same thing is true when you actually look down. If you can skip down to that first, second, third, fourth row where total farm production expenses are, irrigated farms make more purchases of inputs because it's associated with higher yields. You need more seed, you need more fertilizer. Frankly, you'll probably need more pesticides and herbicides in order to produce the value of that crop. And so irrigated farms' production expenses are about $309,000 per farm in 2007. Dryland farms, that's only $77,000. So if you think of irrigated agriculture as also supporting other industries that provide inputs to those industries, things like fertilizers and pesticides and labor and equipment, then irrigated farms actually generate a higher economic multiplier for the local community compared to what those dryland farms are. So why is irrigation important? It's important for meeting global food demands. Irrigation is important for producing food and shipping it to areas where they may have a deficit of water. And irrigated agriculture is important in terms of productivity relative to what we do in dryland production. Quite frankly, we wouldn't be able to meet global food needs or generate as much economic activity if we didn't have irrigated agriculture available to us as an agricultural community. But there are things that are not directly attributed to irrigated agriculture, but are also important because agriculture exists. And sort of relates my first example to that idea of economic activity. In order to orient you, though, I want to tell you a story of Colorado. in particular, and what irrigated agriculture means in Colorado. So this is a map of the state of the Colorado. It's a snake diagram that depicts river systems within Colorado that's been produced by the State Engineer's Office in the state of Colorado. Colorado, being a headwater state, has a lot of different river systems. They include the Yampa, the White, the Colorado, the Gunnison, the Dolores, the San Juan, the Rio Grande, the Arkansas, and the South Platte. On the left-hand side of Colorado, that's what we call the West Slope. It has a population of about 578,000 people and has about 860,000 irrigated acres. But 80% of all of Colorado's precipitation, whether it be falling as green water that crops can use or blue water, and more often blue water when it comes to reservoirs and streams and also groundwater, about 80% of that water actually falls on the western slope where there aren't as many people. The numbers that you see at each of those river systems represent the amount of flow on average for those river systems at the state line. So the Yampa has 1.5 million acre-feet of water a year. The Colorado, our really big river system, has 4.5 million acre-feet a year. Let's compare that to the East Slope, where there's almost 4.5 million people in terms of population. That's the right-hand side of the chart. And there's about 1.7 million irrigated acres, and a lot less flow of water when it comes to this blue water in streams. The South Platte is the largest river system. It has about 400,000 acre-feet a year at that state line. But much water gets reused, and some of it gets transferred from the West Slope to the East Slope. Colorado's like a lot of other states in the sense that they've used direct flows of irrigation water in order to produce agriculture in a variety of different areas. So those areas are generally defined by the water basins. So pay attention to where the South Platte is in the upper right-hand corner, the Arkansas in the lower right-hand corner, the Rio Grande, which is in the central part of the lower part of Colorado, and the Colorado, because I want to talk about the economic activity that's generated by each of those river systems with respect to agriculture. We were commissioned in order to do a study to look at this for some of our state leaders who are grappling with how much water can be kept in agriculture and how that might be done. We have a region in the Arkansas, the Republican River Basin, which is part of that South Platte, the Rio Grande, which was in the central lower part of the state, and then the South Platte, which was in that upper right-hand side. And to gauge the importance of irrigated agriculture to the local economy, one of the first things we did was measure agriculture's receipts relative to the local GDP. So farm gate receipts, sales that are made at the farm, relative to all the regional sales that take place. And you might think of regional sales as being the GDP for that region, or the gross domestic product. In the Arkansas River Basin, remember that was in the lower right-hand part of Colorado, about 31 cents of every dollar of sales can be attributed to farm gate receipts, or sales that happen right at the farm gate. In the Republican, that's 37%. In the Rio Grande, it's very high. That's about 48%. And in the South Platte, that's very low. That's about 2%. It's an interesting statistic comparing the Rio Grande to the South Platte, because the South Platte contains two of the most agriculturally productive counties in the United States. But because this is farm gate receipts divided by regional sales, it's true that there's an awful lot of other things going on in the South Platte, including our state capital, Denver, and other large municipalities. So even though those sales are quite large from farm gates, they're small relative to the rest of the economy. Another way to measure this economic activity of irrigated agriculture and what that might mean to a state is to look at how much is generated per acre of irrigated cropland. When we assessed that value, we found that in the Arkansas, in 2006, a time of lower prices compared to today, we found that there were about $428 per irrigated acre, versus in the Rio Grande, look at that number, almost 3 times as much, $1,127. The difference has to do with what crops are irrigated within that region. In the Arkansas, there's generally lower value forage crops, things like alfalfa hay, that are grown in that area. And that alfalfa hay is generally marketed to cattle, which is not necessarily a high-end market for that hay. Compared to the Rio Grande, there's an additional economic activity, about $1,127, that is attributed to high-value crops like malting barley for beers and potatoes, table potatoes, that get sold all over the United States. But that doesn't tell the whole story of economic activity that's generated, one of the spillovers that's associated with irrigated agriculture. Because not only is there direct activity, which is those sales at the farm gates, but there's also indirect effects. And these are the industries that I talked about that agricultural sales, a dollar of revenue, helps to support in the local community. That includes fertilizer, seed, and chemical sales. But the economic activity only includes the margin or the profit that's produced in that area if the industry isn't headquartered in that area. We want to make sure that we attribute it specifically to the area in which it is. It also includes transportation, trucking that takes place, real estate services, and agricultural consultants who might scout for pests, for instance. Indirect effects are one source of economic activity related to sales, but that even goes further. For those folks that are working on the farms or working in the local businesses, the wages that are spent at the supermarket or in the pharmacy or at the dentist's office, those are called induced effects, and those are also associated with economic activity for irrigated agriculture. So when does irrigated agriculture tend to generate a lot of economic activity? Well, when you produce high-value crops that are sold outside of a region, that brings income in. Or you're able to produce crops that replace imports that might come into your region. It also is associated with when you use a lot of locally produced inputs. That tends to generate a higher economic activity. And local support industries, you tend to use their local labor in order to produce those things. So that's when you produce that higher economic activity. So irrigated agriculture is important in the sense that we meet global food demands, and it's important in the sense that we can shift water to places where we're in deficit. But irrigated agriculture is also an important base industry to a local community. And so if water shifts around or if there's less available to us, that might affect that base economic industry adversely. It's one of the things that we pay attention to as we think about water and agriculture. It's also true that agriculture uses water in a consumptive way, but doesn't use all of the water that way. And also that water might be available because you have to ship it from one place to another for other types of non-consumptive uses. One of the important non-consumptive uses of agricultural water is water that's used by recreation. So those are things like fishing. You see our fly fishermen in the picture up above. Boating, rafting, touring. That might be folks that are traveling up and down in kayaks or maybe touring up and down the river system so they can see wildlife. And hiring guides who can enhance a tourist's experience by being able to see what takes place. Those are all direct activities that also inject economic activity into the local economy. Those spawn indirect activities, just like we had for the agricultural inputs before, and that's the purchase of supplies for each of those industries from local shops. When folks come to that area so that they can raft or they can boat or they can fly fish, they stay in a hotel or a motel, and that recreation industry might not exist without those agricultural water deliveries that we get to recreate on. Restaurants and fuel purchases. So spillovers are not just because of the consumptive use of water in agriculture that supports local industries, but also the non-consumptive uses that exist because agricultural water is used and it's stored and it's conveyed. At the same time, that conveyance may create positive environmental effects, and those might include induced wetlands, so that as irrigation takes place, the runoff runs back to a river system and riparian areas are developed that might not exist otherwise. That creates habitat for important species that might be valued. Riparian areas for healthy ecological systems may be created as a result, and landscapes that people enjoy may be part of the beyond the farm gate benefits of having irrigated agriculture. But that nexus with the environment isn't all positive. Sometimes negative spillovers are created because of irrigated agriculture. And in particular, that might take place because as chemicals or fertilizers are applied to irrigated farmland, and if that water that is used to irrigate should lift those chemicals or that fertilizer off and put them into a stream bed or into a river system or maybe even further on into an ocean, it can impair the environment. And so an important part of addressing challenges for irrigated agriculture is to look at what are the different ways that water quality can be improved. This chart gives you an idea of wetlands water quality state and what those changes are by continent. And the eutrophication or the agricultural pollution or water quality loiled, that percent change is measured on the vertical axis on that left-hand side. And we take a look at it by continent, Africa, Asia, Europe, in the neotropics, into North America and Oceania. And we also have lines drawn across for average agricultural pollution and average eutrophication and quality. So as impairment takes place, there's changes in water quality, and the agricultural lands, because that land has been irrigated and because inputs are used more intensively, can also harm the environment as well. And so beyond the farm gate, there may be those negative spillovers. So we looked at spillovers related to the economy, to recreation, to the environment, all positive and negative, and that's some of the things that we don't actually get a grasp on when we think about agriculture just as food production and as it relates to water. So things are going to change, and one of the things we said at the outset, one of the key points we wanted to take away was that there are external pressures that are going to change the way we do agriculture and the way we use irrigation. And so changes are already taking place in the United States. I like this chart as a way to describe some of the changes that are taking place, and I've circled some instances that are very important to us. So this map is created from U.S. agricultural census data. The agricultural census is just like a population census. Forms are sent out to individual farms, and they write down what they do in terms of agricultural production, whether they use irrigated production or not, the types of crops that they grow, the age of the producer, and other types of demographic information. When we get a census, then we can look at changes over time, and this census takes place every 5 years. So this chart shows, in particular, irrigated lands, which farmers did they use irrigated lands, and the change from 2002 to 2007. Blue dots represent additional irrigated agriculture. Red dots represent a decrease in irrigated agriculture. Both of those dots represent changes of 1,000 acres. So what I'd like to do is start on the far left-hand side and describe some external pressures that are tending to dry up irrigated lands. And those are the red dots that you see. Down in the lower left-hand portion of the United States, in Southern California, and also encompassing parts of central Arizona, there's been a decrease overall, a net decrease in irrigated lands. That's as a direct result of increased demand from growing population areas. So as individuals move into the western United States, homes are built, and those homes and households need water resources. One of the easiest ways to get water resources is to buy them in private market transactions from farmers. As a result, that water is transferred off the farmland, or the houses are actually built on that farmland, but now the water, instead of being used to irrigate crops, are used in homes. And so that's part of the decrease in the irrigated acres. That's a little different than the green circle that you see that's in the center of the page up in northern Colorado. In some of those areas, we've seen a decrease in irrigated acres, in part because of population growth that's taken place in Denver. So population is a pressure, but also because the way laws have been applied in Colorado changed, so that individuals who had wells that were connected to river systems had to go through additional steps and take on additional expense to use those wells. They couldn't take on that expense. The laws had changed, so they shut down those wells, and that constituted a dry up along the South Platte River Basin, which is a basin that we discussed earlier. So that's why those irrigated acres have dried up in those areas. Let's shift down to Texas, which is lower below that dot, where you see I've circled some other areas, especially within the panhandle of Texas. Recall that there were two sources of blue water. One was from surface water irrigation, so rivers and streams, and the other was from groundwater. Well, there's not a lot of rivers and streams in that part of Texas, but there is a lot of groundwater that gets pulled from the Edwards Aquifer and from the Ogallala Aquifer in order to irrigate farmland. And as individuals have captured more and more of that water, they've had to go deeper and deeper in order to get it. And the cost of the energy to pump that water up relative to the value that's created by irrigated agriculture, well, that's gotten to be the case where it's a losing proposition for those farmers. So they've shut down those wells, and those irrigated acres have transitioned to dryland agriculture or gone back to native grasses. So population changes can tend to reduce, that's an external pressure on agricultural water as it shifts to a municipal use. Laws are changing in how we apply water, and that may make less water available for agriculture. And then overuse may be one of the pressures that takes place if we withdraw water from aquifers at a rate that's faster than it gets replenished. And that may cause a decrease in irrigated agriculture, or may cause irrigated agriculture to use water more wisely, to try and conserve water in different ways. Climate change is another means by which irrigated agriculture will feel some pressure related to its water. And when we think about climate change, we think about precipitation change, which I've gotten this figure that's in the middle of the page, but also in changes in temperature, increased temperatures generally associated with climate change, and also longer growing seasons, so you can grow more crops. And also we may see more intense storms and more intense drought events. So all of those things might take place, and generally those will increase the demand that agriculture has for water, so that the amount of crops that you can produce in an area may go up provided that there's water supplies, but that's going to induce increased water too. So we need to pay attention to climate change as an external pressure that will make us use water more wisely, just like population, changing institutions, and depleting water at unsustainable rates may change how irrigated agriculture uses its water. The last innovation that I think has taken place in the last several decades and may continue into the future is the use of biofuels, or using agricultural crops in order to meet future fuel demands, just like we need to meet future food demands. If we're going to be growing more agricultural crops for that purpose, we'll also need to use water in the production of that fuel. There's a water and energy and agricultural nexus in that sense. But also we'll have to grow more crops in order to provide the fodder for those biofuels. One thing we've tried to do is look at what that ethanol water footprint means in Colorado, just so we understand how much water, additional water, is needed. The ethanol water footprint in Colorado, most of our plants operate at about 3.5 gallons of water are needed to produce a gallon of ethanol, and that's been squeezed down to about 3 gallons in some of our more efficient plants. Gasoline, just as a comparison, uses about 2.5 to 8 gallons of water, depending on the technology used in order to produce gasoline. And of course, ethanol is mixed in with gasoline as a fuel that we use in our automobiles. In Colorado's 3 plants, we produce slightly more than 400 gallons per minute, which means we need to use about 595 million gallons per year of water within those plants, which is about 1,825 acre-feet of water within a year. So picture an acre as being about the size of a football field, and think about 12 inches of water being the amount used. 1,825 football fields of water are needed within the plant when producing ethanol. Now, that's pretty small. Think about the surface water that we saw in the snake diagram earlier, of the 4.5 million acre-feet that are produced within the Colorado River Basin, or even the 400,000 acre-feet that are produced within the South Platte Basin. The key, though, is that that's just the water use within the plant. The crops that are needed to grow fuel stock to go into those ethanol plants, well, that's a different story. And so we calculated that too. In Colorado, consumptive use of water, so the amount of water that's needed by the crop in order to produce that grain, is about 1.5 acre-feet of consumptive use. So a bushel of corn needs about 2,600 gallons of water. One bushel produces about 2.8 gallons of ethanol in Colorado, and so one Colorado ethanol facility draws about 20.5 million bushels per year of grain. So the footprint, the grain footprint of an ethanol plant in Colorado is about 20.5 million bushels, which is a footprint of about 163,000 acre-feet of consumptive use water for irrigation. That's compared to 1,800 acre-feet needed just within the plant. So quite a bit more used when we grow those crops. That's about 108,000 acres of corn. It creates an interesting competition with other sectors, and that's what that chart on the right-hand side shows, that if we add ethanol to production in Colorado, there are other industries that need to use those crops, and trade-offs are going to take place about where we route that corn, and probably more importantly, where we route that water. So ethanol is going to compete against the dairy industry, the fed beef industry, lamb industry, the poultry industry, and the swine industry. All of those need about 222,300,000 bushels of corn, or a little over a million acres, 1.179 million acres, in order to produce the corn that's needed in all those industries. Well, the truth is, in Colorado, we can only supply about 148 million bushels of corn, and only have about 785,000 acres of corn within the state in those years. So that means there's a deficit between what total use is and what's produced in Colorado. Where does that come from? Well, it comes from other states that ship it in. So virtual water is being shipped into Colorado to supply a growing ethanol industry as well as animal industries in order to meet the food demands of people all around the world. That's another example of a shipment of virtual water. Colorado's total draw for ethanol, just those 3 plants, is about 325,000 acres of corn, or about 490,000 acre-feet of CU for irrigation in other places. So external pressures, they tend to include growing population is one thing that we've talked about. We've talked a little bit about climate change. We've talked a little bit about using water faster than it can be replenished in groundwater. We talked about changing institutions or laws that affect water allocation, and that'll influence agriculture's use of water. And lastly, we've talked a little bit about fuel uses or new agricultural uses increasing agricultural demand. So what can we do in order to mitigate some of the effects or some of the things that we think are changes that are taking place? Where can we go from here? That's what I'd like to cover next. One place that we're focusing a lot of attention are on the agronomic side of things. Is it possible for us to produce more crop per drop? Because if we're going to meet the needs of a growing population worldwide, we're going to have to find ways, effective ways, to use water. So if we can create crops that can use less water to produce the same amount of grain, we'll be ahead in terms of meeting those needs. This is kind of a neat chart that shows how water is used, green water and blue water, in the plant, where it's stored, how it comes to the plant, where it's stored, and then how it exits. So we get green water via rain that is transpired and used by the plant, and irrigation that's applied to the plant, and that goes through transpiration, which is yield, and some evaporation that takes place. And then some of the water runs off, and then some flows down into groundwater. This is kind of a water balance equation, describing the water equation of how it's used in agriculture. The places that we're trying to improve things are, one, enhancing the ability of the soil to store water for longer periods of time so that it's made available to the plant. And we can do that in a lot of different ways, by increasing the organic matter of that particular soil, or managing the soil differently. If we till the soil less often or not at all, we're more likely to preserve some of that water within the soilscape. We can also reduce the runoff by encouraging infiltration in the soil, and we can do that by amending the soil as well. We might also work within the plant's genomics, or the genetics of the plant, so that it needs less water in order to produce that yield. Or in the case of a drought, there isn't much yield decrease because less water is available. So genomics is an important way to be able to do that too. We also focus on how the crop grows, so that it spends more of its energy and more of its water filling the grain rather than growing the plant material itself. And this is one of the opportunities that we have in terms of scheduling when irrigation might be applied. We'll schedule that irrigation so it takes place in the grain fill periods rather than in the foliage growing periods. So those are some opportunities in order to be able to use water more wisely in agriculture. Not just at the plant level, though, there's other opportunities for us to reduce withdrawals of agricultural water from streams and help to enhance the environment and make more water available to others. And that's by improving our methods of conveyance, so there's less losses taking place, and improving our methods of application, so there's less runoff that's taking place, or that we're timing that. So one of the interesting things that the U.S. National Agricultural Statistics Survey does is to sample farmers and find out what types of technologies that they're using in the field, and then benchmark how that technology changes over time. That's what this chart shows. So as a percent of total irrigated acres, percent of irrigated acres measured on that vertical axis, and then each of the years of this type of survey that's taken place, you can see how traditional irrigated acres by furrow irrigation or flooding the fields is tending to decline over time, and more efficient drip and trickle irrigated acres are being seen as we look across agriculture. That's a savings in terms of the application of water, so less has to be withdrawn, whether that be withdrawn from groundwater or that be withdrawn from surface water systems. Now, the one thing I'll say is that improving efficiency can leave more water in the groundwater, or it can leave more water in the stream, but it also has unintended consequences. Remember, one of the spillovers of irrigated agriculture is producing those induced wetlands, and if there's less runoff that's taking place or less water being applied, there may be fewer induced wetlands, and that may have negative effects as well. But in general, this is a way that we might be able to increase yields relative to the amount of water withdrawn rather than the water consumptively used within the industry. There are other opportunities too for us to enhance environmental effects. In that upper left-hand corner, we've looked at opportunities to alter the timing of pumping within Colorado so that we can enhance habitats in stream flows rather than draw down those stream flows at important reproductive times for endangered species like the brassy minnow. In the upper right-hand side, we've got a group of farmers that are talking about the different types of systems that we might use to conserve the application of water, but also changing crop rotations from, say, a wheat, which is in that far top part of the picture underneath the sprinkler, relative to another crop that's more water using. So by using different types of crop rotations, we can use water more wisely and perhaps share that with other types of institutions like cities and the environment. We can also improve water quality by using things like vegetative buffer strips to reduce fertilizer runoff. And we have government programs that help us to be able to do that. So we can enhance water quality so that it's more usable by municipalities and it's also better for the environment. And we can take care of our headwater areas that are in the lower left-hand quarter, where if we restore forest, especially after the advent of fires, we can improve water quality so that it's easier used by agriculture and the environment and for municipalities. So there's some different ways that we can approach some of the challenges of the future that we face because of external pressures that are going forward. Well, this has really been an introduction to a lot of issues related to water and agriculture, and I hope we've been able to drive home some key points about the complex nature of water as it's used in agriculture and how that relates to other industries. The way that agricultural water will necessarily have to change because of climate change and increasing populations, and also because of the way institutions are changing and because of some of the other challenges that we face. But those challenges have created opportunities for us, opportunities related to genomics, related to increased technology, the way we manage water systems, and the way we take care of water systems so that we can meet those future challenges.